This is part 6 of the lecture, Linear Systems and their Diagonalisation. So here we'll go through the convolution theorem, which leads to a first reconstruction methodology for the backprojected PET data that we've looked at in previous parts of this lecture. Then we'll look at convolution in matrix vector form and then show how the Fourier transform nicely diagonalises the convolution matrix. So you'll recall that we have some object inside the PET scanner field of view. Here we've got a collection of point sources, and when we acquire data during the PET scan and then back project that data, we get some result such as the one shown on the right hand side here, which we're calling the back projected image. Effectively, it's been modelled by a forward projection and a back projection to arrive at this situation here, where each point source in the input, in the field of view, in the object of the scanner, each point source is getting replaced by a point spread function. And that is well modelled by the very familiar convolution integral, which I'm showing here in just one dimension, where what happens is the input function here, that's the true object on the left-hand side there, that's f in here. We just visit every spatial position here in 1D, just denoted by x prime. Visit every position, find the intensity or the amplitude of the point source, that's f in, and then use that as a scaling or a weighting factor for h of x. H of x is the point spread function or the point response function. So we can see one of them here. Look at that point there. That gets replaced by a point spread function. So h of x would just be one of those shaped response functions. So for every single point source location with a given intensity f in, we use that as a scaling for the point spread function h of x shifted to the position x prime of the point source that we're considering at that very position x prime. And then we sum over all of those positions x prime to arrive at the final output back projected image, which is what we're seeing on the right hand side there. So that same formula can just obviously be extended in 2D and 3D, and then also applies, for example, in this case here, where we've got the Shep-Logan phantom, just a collection of point sources getting replaced by point spread functions. And then remember this special case here, where if the input object was a 2D sinusoidal function, then when it goes through that acquisition process and the back projection, then we get exactly the same function out the other side, but just scaled by some scaling factor. And so that is a very good motivation for using Fourier analysis. Okay, so let's now look at what's called the convolution theorem. That was the convolution integral that we just looked at on the previous slide and what we looked at graphically as well. Now let's consider the case a bit like that bottom row of the previous slide where we had the 2D sinusoidal function. Let's now explicitly put in a complex exponential. Okay, so that's going to be cos k0 x prime plus I sine k0 x prime. Okay, so that input function there, f in x prime, we're replacing it now explicitly by just one complex exponential. And then all the rest of the convolution integral is staying the same. Okay, now we're relying on something that I'm not going to prove here, but that convolution is commutative, which means here we could interchange the f in and the h and end up with exactly the same output. So this f out could have been h of x prime, f in x minus x prime, and we'd get the same result. So that's all that we've done here. We've just now put h x prime for the input and then put that single complex exponential in as if it was the point spread function, but of course we're still keeping an eye on the fact that that h is the PSF, the point spread function. Okay, so those two equations are identical. Now if we just note that this integral is only going over x prime, and here this complex exponential has an argument involving x prime, so that needs to stay inside the integral. But we've also got this component e to the I k0x. Oh, I should say, of course, that k0, the reason I'm saying that is that's indicating one single fixed spatial frequency as written there, single spatial frequency k0, so just one choice of a complex exponential. So that k0 multiplied by x is independent of that integral over x prime, and so we can factor it out, like I've done there on the left-hand side, factor it out of the integral, leaving behind the integral over h of x prime times e to the minus I k0 x prime, dx prime. Okay, and so this is now looking very interesting. Hopefully you can recognize immediately that that is none other than the Fourier transform of the function h. Okay, we can use any dummy index that we like for the integral here, so that's as good as that is the Fourier transform of h of x, or h of x prime, whatever index, whatever variable we want to use to access the values in that point spread function. But notice it's actually evaluated for that fixed single spatial frequency k0, so that's why we're showing this function capital H, okay, dependent on just that fixed value k0. But in principle, of course, we could have plugged in any particular spatial frequency k, and then we just know that this is just given by the Fourier transform of that function h of x, Fourier transform of the PSF. And so that's where we get our nice familiar expression, where remember we're talking about the complex exponentials being eigenfunctions of the convolution operator, because when you put this e to the ikx through a convolution, the output is also that very same function. Look at that, e to the ik0x, which is the same as the input, e to the ik0x or x prime, whatever independent variable we're using to access the function. It's an identical function, just scaled by this factor h, which we now see turns out to be the Fourier transform of the point spread function. That's commonly known as the transfer function for obvious reasons, because we can see how a spatial frequency is transferred through the convolution with just a scaling factor associated with it. We're seeing at another video that we can come up with a concept of the modulation transfer function, but really when you just Fourier transform the PSF, you could just call it the Fourier transform of the PSF or call it the transfer function. It's up to you. Okay, so that's showing the case of one complex exponential being convolved with a point spread function. Shows nicely that the output is the same function with just a scaling applied to it. Okay, so that's just rewritten here. If you put a complex exponential in, then the output is just that same complex exponential with just a scaling factor in front of it. Now, of course, in general, those scale factors could be complex, but all that will do is it will still keep exactly the same frequency. It could just be phase shifted according to the relative weightings between the sine and the cosine for the imaginary and real parts of that complex number of h, the scaling factor. But just think of it as a scaling factor. Now, in general, of course, we're interested in general input functions and not just complex exponentials. But then we know by Fourier synthesis that a general input function can be expressed as a summation of many complex exponentials. Okay, that's what the inverse Fourier transform tells us. So here is an expression for Fourier synthesis, the inverse Fourier transform, where we're saying any object, any input function that could be inside our PET scanner field of view is just equal to a summation over infinitely many complex exponentials. So in other words, all of the frequencies from minus infinity up to plus infinity, each of them with a unique weighting factor, a unique scale factor or a unique coefficient that allows us to recreate, to synthesize that original object. Okay, so the weighting factors for each of those complex exponentials are absolutely crucial, of course, to arrive at a particular choice of input function. So, in more simple terms, you can think of this as a generalization of the Fourier series, of course. It's just that this is now for aperiodic functions rather than periodic ones. Okay, so then what happens when we now put that general input function through convolution? Well, we know already from what we've just looked at before what will happen to a single complex exponential. And now we know that if we're expressing our input as a collection of complex exponentials, then we know that each one of those is just going to be uniquely weighted by h evaluated at the particular frequency of each complex exponential. So it really is a very straightforward process. So that's what I've written here. For the output, each weighted exponential, in other words, these are the weighted exponentials of a given frequency k, is simply scaled by the transfer function at that particular frequency. So therefore, the output of a convolution, here we are, we've just got exactly the same expression for the input function here. The only difference between the expression for the input and the expression for the output is that we've just put inside this scaling h of k. Okay, so we think of these complex exponentials as eigenfunctions, or in the discrete case, eigenvectors, and then we can consider the h as the eigenvalues for each of those eigenfunctions. Okay, and then we can see immediately that if we Fourier transform both sides, then the Fourier transform of the output function we're just going to denote as capital F of the output function. And then here, knowing this is already the inverse Fourier transform, if we Fourier transform that, what we'll get are just the coefficients for each and every one of those complex exponentials. Well, we know, here's the complex exponential. What's its coefficient? Well, it's f in k multiplied by hk. That is the net product that gives the single coefficient for that complex exponential. So that's why we've written in f in k times hk. So that is the convolution theorem saying that with the previous slide, maybe I'll flick back to that quickly, there was the original expression for convolution, and now with this, when we Fourier transform that expression, we end up with a purely multiplicative expression. So instead of convolving f in with h, if we go to the Fourier domain, we just multiply the spectrum of the input object by the spectrum of the point spread function, in other words, multiplied by the transfer function, and that will give us the Fourier transform of the convolved output. And so if we want the convolved output, we can just inverse Fourier transform that, of course. And so coming back to our back-projected PET data, this provides for a very simple way of reconstructing the data. And in fact, this goes way, way back to a publication in 1977 for 3D back-projected PET data. So there's our familiar convolution integral. I won't talk you through that again. I think you can understand that quite clearly, especially with the visualization here. So, okay, the collection of point sources convolved with the PSF gives the back-projected image. We know by what we've just looked at that we can Fourier transform that, and this is the Fourier transform of the back-projected image, and we're saying it's equal to the Fourier transform of the unknown object, because of course when we back-project PET data, all we know is that we've got a back-projected output. And then of course what you can do is put a single point source inside your PET scanner, and you can measure the point spread function. So you could measure this, and then when you put in a general test object or a patient that just goes into the scanner, then you could back project the data. This is not done these days, but this is a very instructive algorithm to understand. But what you could do is back project the data, even though actually with time of flight these days, they're beginning to now move towards time of flight back projection and then plugging that into machine learning. So it's kind of funny how these things come back into fashion again. But anyway, this would be the back projected patient data, and we're expressing that as the unknown true object convolved with a known point spread function. And then all we have to do is Fourier transform the known point spread function, Fourier transform the newly measured back projected data, and then the only thing that we don't know is the Fourier transform of the true object. So how can we find that? Well, it's obvious. If it's just a multiplicative relationship like that, then we can just do a division. So F is equal to G divided by H, and then we just inverse Fourier transform that, and that will give us a reconstruction of the object that was inside the PET scanner field of view. Now, of course, this whole model depends on convolution holding, and so therefore it does require the point spread function h to be shift invariant. So in fact, that should be a lowercase h to be strict, because capital H I'm using here to denote the Fourier transform of the PSF h. Okay, so this should be lowercase. So hopefully that's clarified a very simple approach to reconstruction. It's effectively doing a deconvolution. Now to really get on to some of the mechanics of what's going on there and to understand what Fourier is doing to help us there, let's first, this is a very simple slide I'm about to show you, let's just visualize the convolution operator in matrix form, okay? So in the previous slides we've been dealing with continuous functions. Let's get back to discrete vector, the vector case now. So now we've got an input vector f, remember that's just a list of numbers which when rearranged gives us a 2D image. And then it's going to go through a matrix H, which is going to be a convolution. Okay, and we're now going to show you what's inside that matrix H for convolution, but hopefully you can already begin to figure that out, and that will deliver some output, that's like our back-projected image, G. Okay, so let's go through this for a very simple case of a 5 by 5 pixel image. So we know we've got 5 by 5 pixels, that's a list of 25 numbers. So the input vector f will be a list of 25 numbers. The output vector g will be a list of 25 numbers, just a 25-dimensional vector. And so that means the columns of h are also going to be vectors of 25 dimensions as well, just 25 numbers in a column. Now we know what's happening with convolution. Each of the points inside f, each of the point source intensities, is getting replaced by a point spread function in the output. So that means all we need in the matrix H is just duplicates of that point spread function just shifted to various positions. And so that's what this very simple illustration, this animation is showing you. All I've got there is a shifting simplified kernel. I've just got a kind of intensity 2 with side lobes, first order side lobes of values 1. And then each of those positions of the kernel just gives us a unique 5 by 5 image of the kernel. And then all I'm doing is just copying those 25 values into a column of the matrix H. And so that is what the matrix H would look like for convolution. There is a slight caveat here, which is that, as you'll see right in that very finishing position of that kernel, maybe I'll just run that again. You can see here I'm actually clipping the kernel at the edges as it's going through. Now here you can see the whole kernel, okay? And there it's clipped, but here it's the whole kernel, whole kernel, whole kernel, and clipped. And because of that clipping, when you scan across the values in this matrix, you'll notice that there are some 0 values kicking around. And so that means strictly this is not a convolution matrix, and what we should have done would be to duplicate that input function everywhere and then just have the kernel wrapping around. So in fact, well, to be clear then, we could still keep our input vector of 25 values, but for the convolution theorem to hold, for the discrete Fourier transform to be applicable, then we'd need to allow the wraparound here, back round to the top. We need to allow the side lobes of that kernel to flip around to the other edges. Okay, so and that does give rise to all kinds of ways of needing to deal with that problem, such as zero padding, such as duplicating your image, whatever method it is, but you do need to be careful with edge effects when it comes to convolution. Okay, so that's what I'm saying here. Here we've clipped the kernel at the edges. Strictly convolution uses a circulant matrix, okay, and that's one where all of these diagonals would be strictly identical. We wouldn't have the zeros in there. We'd have ones all the way down cleanly and the 2 all the way down the diagonal there. This is just a 25 by 25 matrix. And then, as I say, these values here would lap around back at the top. Okay, so now we're getting to the whole concept of diagonalisation. So that's what you've just seen. Now we've got an output vector G is just a convolution matrix, just duplication of the point spread function, discretized and shifted to every single position in the field of view. And then the input vector F is regarded as a collection of point sources, which are just weighting factors for each of those PSFs, all the different positions, and that gives us the output. Thanks to the convolution theorem, we can Fourier transform this back-projected image G, so I'm calling that this kind of small capital G there. We can Fourier transform the unknown object F, And we can also deal with a diagonal matrix now. Okay, so this is quite subtle. H was a very dense matrix with duplicates of that kernel. What we know by the convolution theorem is that we can Fourier transform that point spread function to get the transfer function, and that's why I've called this a matrix capital T, because it is a diagonal matrix, and all we have down the diagonal of that is the Fourier transform of the PSF. Right, and so this G equals TF is just a simplistic point-by-point multiplication in the Fourier domain. So writing that in matrix vector terminology now, that means this F here is the Fourier transform of the input. So we know before from the discrete Fourier transform, that means S star F is the Fourier transform of the vector F. The diagonal matrix T stays the same, and this small capital G was just the Fourier transform of G, and so we can get the Fourier transform of G by doing S star on G. Okay. Now we can inverse Fourier transform both sides, and that means just apply the matrix S. That just contains all the columns of all those complex exponentials that we've seen earlier on in other parts of this lecture. Applying that to both sides, and we know, thanks to the properties of the Fourier transform, inverse Fourier transform, that this S star just is the identity mapping. So we're just left with G is equal to S TS star F. And now take a look at this, compare it to the top, and you can now see the whole principle of diagonalization, which is that our convolution matrix H is equal to three matrices. The first matrix does the Fourier transform. The second matrix just does a simple point-by-point multiplication because it's a diagonal matrix. And then we inverse Fourier transform. So if you want to do a convolution, we know already by the convolution theorem that all you have to do is take your function, Fourier transform it, multiply it in the frequency domain by the Fourier transform of your point spread function or the Fourier transform of your impulse response function, whatever language you're using for your convolution. And then once you've done that, you inverse Fourier transform. And that was equivalent to applying a convolution with that impulse response function or with that point spread function. So visualizing diagonalization, we get this situation here. So that's what we've just seen on the previous slide. And so this is just an illustration, okay, just to get the concept. Got an input vector here, only 5 elements, and here we've got the Fourier transform. Again, this is just an illustration. This should have the zero frequency and so on. You get the idea. It's just showing the increasing frequencies of the complex exponentials. So this does a Fourier transform. And then once we've Fourier transformed, that will give us the spectrum as, if you like, a 5x1 vector, for which we can then apply this diagonal matrix, which, remember, contains the transfer function just down its diagonal. That's the Fourier transform of the point spread function, or the Fourier transform of the impulse response function. And that will just multiply each of the coefficients of each of those basis functions that were present in that input vector f. Once we've done that multiplication, we can now inverse Fourier transform. So by this point here, we've now got, again, a 5x1 vector in the Fourier domain still. And then that 5x1 vector just operates as a set of weighting factors for 5 complex exponentials. Again, remember, this is just an illustration. There should be the zero frequency and so on. So 5 weighting factors for 5 complex exponentials here. We add them all together, and that will give us the output, the convolved output, which is a vector G. So using a very crude illustration at the bottom here, there's the input vector f, just so that's actually far more than just 5 pixels, so this would be a much taller vector. This then is the Fourier transform matrix, that's just showing the real part of it. And here I'm showing by the blue line, it's actually the modulation transfer function. It's just a normalized version of the transfer function, but just is sufficient for our purposes to show the classical case, and that's what I'm trying to show here, of decaying values. Okay, so what happens is the higher frequencies get attenuated in most imaging systems, whereas the lower frequencies pass through hopefully relatively unaffected. Anyway, we get this kind of decaying spectrum of the transfer function. And then once we've applied that to effectively achieve the convolution, but albeit in the Fourier domain as a point-by-point multiplication, then we've inverse Fourier transform. So in fact, that would strictly be the conjugate transpose of this matrix here. So ignore that top part there. And then that would give us the output, the convolved output, in this case G. Okay, so just representing that here, it's a lot more than just the 5 elements there. And then that also suggests an obvious reconstruction formulation. There is our diagonalized H, G equals HF, but diagonalized, that means F is just the inverse of those 3 matrices. So just by the rules of matrix algebra, we achieve the inverse by reversing the order and doing the inverse on each of them. So inverse of S, well, S is the inverse Fourier transform, so its inverse is the Fourier transform, S star. Inverse of T, now this was the whole point, otherwise we would not have done this. T is diagonal, and so therefore its inverse, T minus 1, is extremely simple. You just take the reciprocal of all of those elements in the diagonal. And then finally, inverse of the Fourier transform, S star, that's S. Okay, so S went to S star, T went to T minus 1, S star went to S, and that gives us the reconstruction F. So you take your back-projected image or your convolved result that you're wanting to deconvolve, Fourier transform it, apply the inverse of the transfer function to it, and then you inverse Fourier transform, and that gives you the object. So that would be equivalent to doing the following in practice, which would be find the spectrum of your back-projected image or your convolved image, the spectrum G, and you need to just divide that by the spectrum of the point spread function or the spectrum of the point impulse response function. And then what I've done here is I've just multiplied top and bottom by the conjugate of H because that gives us a purely real number in the denominator, which helps with this complex division. And that gives us the spectrum of the true object, which we can then inverse Fourier transform. So in summary, over the entirety of all the parts of this lecture, we've covered images as high-dimensional vectors, we've looked into matrices, we've considered object representation parameters, and then crucially we've seen that some imaging systems can be described as convolutions. Convolution can be diagonalized by the Fourier transform, which gives us a really easy way of reconstructing. If a mapping is not linear shift invariant, then in general for a linear mapping, in principle, but not very much in practice due to the difficulties, which we'll mention in another lecture, in principle, the singular value decomposition would really be the beautiful way of handling all kinds of linear mappings. And in fact, it does give a lot of insight if your system and data are small enough to be dealing with a SVD, a singular value decomposition. Anyway, thank you for listening to this series of parts of this lecture. Thank you.